Now on this video I'm going to finish up the idea of atomic bonding with review of the different kinds of bonds and their relative strength. Remember, to review what we talked about in the previous video, that ionic bonds are going to be transfers of electrons between atoms which have very differences in electronegativity. So usually between a metal and a non-metal, and the electron actually gets transferred. While if the two atoms have very close electronegativities, then you're going to have electron sharing, usually between nonmetals, and you're going to form things like single, double, or triple covalent bonds, or even polar covalent bonds, which are almost ionic bonds, but not, the electronegativity difference was not strong enough to make one atom rip the electron off the other. Now, in terms of bond strength, okay, or how much energy each of these bonds store, the strongest of bonds is going to be the ionic bond, and that's because it's got those charges. The ionic bond creates actual charges. So there's going to be a very close electromagnetic interaction between the ions, the cation and the anion, which will actually hold them together extremely strongly. Now you're going to have some ionic bonds which are weaker than others, and as you go down you're going to become less and less ionic until you get things like polar covalent bonds, where you don't have real charges, you're sharing the electrons. So some of the time you have a partial, so it's going to be partial charges, and that's going to be a little stronger than the covalent bonds. Okay, you also have some very, very weak ionic bonds which are actually even weaker than polar covalent bonds, but those are very, very rare. You're not going to see them very often. And then under that you have the nonpolar covalent bonds. In the order, they're going to be triple, double, and single covalent, because there's less and less electrons that you're sharing to make those bonds strong. So what's the most strong bond between atoms in nature? Ionic bonds. Then followed by some polar covalent bonds, followed by some weak ionic bonds, followed by nonpolar covalent bonds. What that means is that compounds which are held together by ionic bonds will tend to be solid at room temperature, since they'll be attracted very strongly to each other, while compounds held by polar covalent bonds are more likely to be kind of liquid, and compounds bound together by nonpolar covalent bonds are more likely to be gaseous, because there's very weak attractions between the molecules. And we'll talk more about that in the last video of the lecture series. We talk about intramolecular forces. Alright? Now, that's basically the bond strength. And to review the different kinds of bonds, you have ionic, covalent, and metallic. Ionic is going to be forming cations and anions through transfers of electrons. Covalent is going to be calling pairing of nuclei and sharing electrons, and that's going to actually be sometimes polar, sometimes nonpolar, sometimes single, double, or triple covalent bonds. And you have metallic covalent bonds, where you're going to have delocalized electrons, and those are those weak ionic bonds that we talked about, which are in between the polar covalent bonds and the non-polar bonds. Okay? Now the kinds of bonds you have between the atoms are actually going to help determine the kinds of bonds you have between the molecules as well. Okay, so let's talk about this. For example, the ionic bonds, because you're going to have charges forming. So let's say, for example, I'm going to write down all the negative charges here in red. So you have negative here, negative, 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 negative. All of these are going to be negative charges. Okay, whoops. All of these are negative charges. And then you have all the positive charges. Okay, so do you see a pattern forming over here? You see how every single positive is connected to a negative, which is connected to a positive, which is connected to a negative, which is connected to a positive, which is connected to a negative, both vertically and horizontally, which helps create a crystal, which maintains a solid structure for these things, which why salts are more often than not solid, because they're made of ionic bonds between a metal and a non-metal. And you see that's a perfect example of sodium chloride here. Alright? Now, in the case of covalent bonds, you're going to form other kinds of structures which are going to be weak interactions between the molecules, and we call those van der Waals structures. So instead of crystalline ionic structures, you call van der Waals forces. Now, I remember this because that's why the geckos used to climb the walls. They actually create polarization of their paws, and they create like an electromagnet in their paws. And using the electromagnet of their paws, they actually attach themselves to slightly partial charges at the walls, allowing themselves to stick to the walls. The same way, polar bonds and other types of covalent bonds are attracted to each other to interaction between areas of the molecules which are actually partially charged. For example, in the water molecule, remember how you have some areas which are negatively charged. For example, all the oxygen areas are going to be negatively charged. And then you have all the positive areas which are going to be positively charged, or the hydrogen atoms, right? And so what's going to happen is that all the positive will be attracted to the negatives and will form something that's almost the same kind of crystalline structure that you will see in the specific case of the crystalline structures. But since it's caused by partial charges, it's just a van der Waals force or an attraction between this, okay? In the case of water, this van der Waals force is happening between an atom like oxygen, which is very electronegative, and an atom which is not electronegative at all, like hydrogen, all right? There are three cases when things like this will happen. Whenever it's hydrogen versus nitrogen, hydrogen versus oxygen, hydrogen versus fluorine, and even, sometimes, rarely, hydrogen versus chlorine as well. Now what this will create, these are the most electronegative atoms in nature, and what this will create is a van der Waals force that's so polarized, it's so strong, that electrons from this hydrogen are sometimes displaced towards that oxygen, which creates a very strong kind of van der Waals force. Now, all van der Waals forces are weak, but this particular van der Waals force is slightly stronger than the other kinds of van der Waals forces, and we call them hydrogen bonds. And these hydrogen bonds are the bonds which are going to give water its special properties, like high specific heat, high heat of vaporization, surface tension, cohesion, adhesion, solubility, universal solvent, all these kinds of things. And notice how those covalent bonds and those hydrogen bonds are going to be creating a crystalline structure in the water molecule, which helps the water molecule retain its integrity, creating all those kinds of bonds. Those same kinds of hydrogen bonds exist between proteins, which hold the proteins together. It also exists between the strands of the DNA molecule, which hold the DNA together. So these hydrogen bonds are going to be very important for life. But remember, these are just special, slightly stronger kinds of van der Waals forces, which happen when you have a very electronegative atom attracted by van der Waals forces to hydrogen, basically. All right? Now, remember, this is actually very weak, and by themselves, they are very, very weak. But when you put a lot of these hydrogen bonds together, you can actually feel their effect. For example, all your DNA is held by these bonds. All of water is held together by these bonds, and so forth. And all the proteins are also held by these bonds. Now, when it comes to bonds or intermolecular forces between covalent bonds, especially the non-covalent bonds, it's going to be a little more tricky. Now, you don't need to know this in too much detail, okay? You'll do it again when you get to the actual chemistry. But what I wanted to point out is that as you go down here, it's going to be weaker and weaker attraction between molecules. So, for example, there's going to be a slightly strong attraction. Obviously, ionic bonds are going to be the strongest, and they're not even featured here, okay? But that's because ionic bonds are between atoms. All of these are intermolecular forces, or between molecules, while things like covalent bonds and ionic bonds and metallic bonds are going to be intramolecular forces, or forces inside the molecule. We're talking about forces outside the molecule here. But if you put an ion versus another ion, you're going to get the strongest kinds of attractions, because it's going to be what we talk about, forming those crystalline structures. Second to that, you're going to have things like ions connected to polar covalent molecule. All right, so an actual charge connected to a partial charge kind of thing, and that's called an ion charge dipole charge connection. Then you're going to have things like hydrogen bonds, which form between a very polar molecule and a hydrogen. Okay, we just talked about that. Then you have connections between polar molecules, which are not necessarily hydrogen bonds, and look, like I said, nitrogen, oxygen, and fluorine are the three examples, but sometimes chlorine as well. These here are going to be just basically between two basic polar molecules. It's called dipole-dipole because it has poles within the molecules. This one is going to be between an ion and an induced dipole. Now, What an induced dipole means is that this molecule here was not polar, but because it came close to an ion, it became polarized. So that's going to be weaker than that one right there. Now, similar to what happened there, you could have one molecule inducing one that's nonpolar to become kind of polarized. And again, you have the same effect that over there, but since this was an actual charge, and this is only a partial charge, the ion-induced dipole is going to be stronger than the dipole-induced dipole. Okay? And then you have attractions between two nonpolar molecules. And those of you are very, 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 very weak, and it's only going to be caused by transient charges as the electrons kind of float around and create a slightly area of the molecule which is slightly more negative transiently. So those things are often what holds gases together, kind of thing. Very, very weak attractions between the molecules. Alright? And you see examples here of molecules which are held together by these kinds of forces, and the amount of energy in joules these forces actually stores. This picture actually reviews the concepts that we've been talking about. For example, if you have interacting molecules or ions, you ask yourself, are ions involved? If there is, then you have to ask yourself, are polar molecules involved and ions both present? If not, you're talking about connections between ions, and that's going to be very, very strong and form crystalline structures. But if you have both an ion and a polar molecule, that's a covalent bond, then you're going to have the ion-dipole forces. If you don't have ions involved at all, then you're talking about just maybe polar molecules. If the polar molecules are involved, if you have hydrogen bonds, you call hydrogen bonding. And that's if you're going to have a hydrogen atom on one end of the one molecule, and then a nitrogen, an oxygen, and a fluorine on the other one. So we call them bonds. And that's going to be hydrogen bonding. If you don't have the hydrogen bond, you get a slightly weaker polar dipole forces interactions. Now, if there were no polar molecules involved, you're going to get London forces only, or induced bipoles. And there's three types of those induced bipoles which are not actually listed in this particular one. One is induced by an ion inducing a nonpolar molecule to become polar, and that's going to be the strongest. The other was induced by a polar bond inducing it. And the other last one is basically transient induction between two nonpolar molecules, which is going to be the weakest kind of interacting molecule forces. But remember, any of these last three are called van der Waals forces. It's the cause of forces whenever you don't have an ion involved. So that's kind of bonding, and we just have one more lecture series when we talk about chemical reactions and chemical equations. I'll see you guys then.